Okay, Algebra 1, we are going to take a look at applications of proportions, and that's section 2.8. So if I go here, one of the most common ways that we use proportions is with similar figures. So I believe we looked at this in 7th grade, but if we know that figures are similar, which means that they are the same exact shape, just increased or decreased in size. So not just one side increased, but everything is increased and they stay proportional. So what they use is they use this little till sign, I call it. So they say that triangle HAL is similar to triangle NED. They're not equal, they are just similar. So if you can match up corresponding sides, you can use proportions to find missing lengths. So for example, I made this table for us, and we have triangle HAL and NED. So the first 2 points are HA and NE. So let's fill this out. HA is 12 inches. NE is 3 inches. So even though these triangles are in different orientation of each other, we can still find this information just by the names of the triangles. So AL is 5 inches, and ED we do not know. Okay, and the next one is HL, that's this long one, 13 inches, and then ND is a 3.25. So the cool thing is that we know we need to find these. We need to use these 2 pairs. And then the nice thing is when using a proportion, you can use either one of the other 2 pairs. Now, I personally like to take nice numbers when I set up my proportions, if I can. So I'm going to use the first 2 points. So they have this little proportion for us. HA is to AL, so 12 is to 5, as 3 is to X. So here, HA and AL are both from the same triangle, and NE and ED are from the same triangle. So I'm going to take 5 times 3, and I'm going to divide it by 12, and I get 1.25. So X equals 1.25 inches. And there we just solved for our missing side. Of course, you always want to check to make sure it's proportional, but it will be. And I wanted to show you, I can use the other 2 if I wanted to. So I'm just going to put an OR here. 5 is to X, as 13 is to 3.25. Well, let's just do the math. 5 times 3.25 divided by 13. And I get the same answer, 1.25. So like I said, it doesn't matter which one you would use. Okay, so let's go to this one. It says triangle ABC is similar to DEF. So I'm going to use my first 2. AB, right here, is similar to DE. Okay, I'm going to use different colors. And then BC would be equal to or similar to EF. BC, right here, and EF. So these ones are hard to figure out, so it's good to have the label there. And then my last one, use the first like A and C right here, and D and F right here. So now that I have the sides kind of matching, I can set up my proportion. You have to use the side that you're missing. So I'm missing this one. I have to use that. So maybe I'll even start that way. So I like to, if I have 2 shapes, sometimes it's nice to do the work right underneath them. X is to 12, as, and then I can use whichever ones. I'm going to use the 13. 13 is to 10. So if I solve this, 13 times 12 is 156 divided by 10, I get 15.6. So x is 15.6, and then we do have a label of feet on there. There we go. Okay. Now our next shape, I didn't transfer, but it's lady is similar to gent. Now this one is probably a little bit easier to see which sides go together without even needing the reference of their names. This long side goes with this long side. Let's see what other colors I have here. This short side goes with that short side. The opposing side goes with this one. I'll just leave that top one blank maybe. You guys can see her all just. Okay, so like I said, you need to know which two sides you're missing, or which side you're missing. So I'm missing my x. So if I would start my proportion, 3.5 goes with my x, and then you have to pick two other sides that you have. So for example, I couldn't use the blue side because I don't know what that is here, but I can use the yellow. Once you have your proportion, 3.5 times 3.5 divided by 2 gives us 6.125, 6.125 centimeters. Does that seem reasonable? What side am I missing again? Yep, right here. Well, it is the longest side, and 6 would be longer than the 3. So yes, I would say that that seems reasonable, like a reasonable answer. Okay, my next couple, I like to draw little pictures lots of times. So it says a totem pole casts a shadow that is 45 feet long. So let's draw our totem pole here. Maybe we've got this pole. I feel like lots of times they have like an eagle or something. Oh goodness, my eagle. Told you guys I was a great artist. There's my totem pole, and it casts a shadow that is 45 feet long. So this shadow is 45 feet. At the same time, a 6-foot tall man, so we know that this guy is 6 feet tall, and he casts a shadow that's 3 feet long. So when I set up these proportions, I always like to do shadow to actual. The actual is always going to go on the bottom when you set up a proportion. So the shadow of the guy is 3. His actual height is 6. The shadow of the totem pole is 45, but we don't know the actual height of that totem pole. So 45 times 6 divided by 3 gives us 90. So that means that that totem pole is 90 feet tall. And I'm sure some of you could have looked at that and been like, okay, well, if the guy is twice his shadow, the totem pole is going to be twice his shadow. But sometimes they're not as nice, so being able to find those answers is helpful. The next one, a forest ranger who is 150 centimeters tall casts a shadow that's 45 centimeters long. So I've got a forest ranger. Maybe give him a cool hat, right? Forest ranger hat. And he is 150 centimeters tall. He's going to cast a shadow that is 45 centimeters. At the same time, a nearby tree we cast a shadow that is 195 centimeters long. So again, shadow to actual. So the guy, his actual height is 150. His shadow is 45. The tree, we don't know the actual height of the tree, but we do know the shadow of the tree is 195. 195 times 150 divided by 45 gives us 650, and we're working in centimeters, so the tree is 650 centimeters tall. Okay, let's see. We are going to talk about scale factors, so changing dimensions. So it says when you multiply every dimension of a figure by a scale factor. So the scale factor is what you would multiply by it to change its size. So for example, if I were going to make something larger, I would multiply it something by like 2 or 4, and it's going to be 4 times as big. So the scale factor would be 4. If you're going to make it smaller, you'd multiply it by a fraction or a decimal. So if you multiply all the dimensions by something, you will create a similar figure. So it's going to have the same shape but different size, and you can, determine the scale or the ratio by thinking about the units that are used to measure the perimeter area and volume. So basically what they're saying is that if you just change one dimension, so like perimeter is just the area around, that's a single ratio. So it just has the same effect. So if it was 4 times bigger, the perimeter is going to be 4 times bigger. But when you change the area or the volume, it's going to have this like doubling or tripling effect because you're changing more than one dimension. So this might be kind of confusing, but we'll just do our best to get through these notes and then we can go from there. So some nice examples here. It says the dimensions of a rectangular cake measure 12 by 18 by 4. Every dimension is multiplied by 1/2 to create a smaller, similar cake. So we don't want to change the shape, we just want to change the size. So if we were going to change the size of this by 1/2, it would go to a 6, a 9, and a 2. Okay, so this is something that's 3-dimensional. So originally, the volume, I'm going to take the volume as all sides multiplied by each other, 12 times 18 times 4. And I get the volume of the original was 864. The volume of the new is 9 times 6 times 2. So 9 times 6 times 2, and I get 108. So they want to say, how is the ratio of the volumes related to the ratio of the corresponding dimensions? Well, the ratio of the dimensions is 1/2, 1 to 2. You took and cut it down by 2. But the ratio of the volumes is actually 108, because that's your new volume, compared with the 864 that it was originally. So the best way to do this is just to put it in as a fraction, 864, and reduce it. So do you see it gets to be 1/48? Oh, sorry, 108. I was like, that doesn't seem right. Over 864. So it gets to be 1/8. So what they're asking is, what is the ratio of the volumes related to the corresponding dimensions? So look at here. That's the volume. This is the dimensions. Volume, dimensions. So what is the relationship between 1/2 and 1/8? Well, the volume is 3 times the ratio of the dimensions. So we took 1/2, but because we are relating it to volume, and volume is 3 dimensions, we had to take that and we would get 1/8. So I know it's kind of confusing, and remember, it's always like new shape to old shape, like model to actual, that type of thing. So we're gonna fill in here and try to give you guys some more examples. So the scale factor is 5. So the ratio of the perimeters is just 5. Okay, it's kind of like 5 to 1. So 5 to 1 is equal to 5 though. So then the ratio of the areas is that squared because it has twice the effect. So 5 times 5 is 25, so it'd be like 25 to 1. Well, the ratio of the volumes is 3 times this, so it'd be 5 cubed, which is 5 times 5 times 5, which is 125 to 1. So if you multiplied like a cube and you took the side of it and you multiplied it by 5, the ratio of the area to the original would be 25 bigger, and the ratio of the volumes would be 125 times larger than the original volume. So that's what's kind of interesting. It just has such a bigger effect. So the ratio of the perimeter is 2/3. So the ratio, or the scale factor is 2/3. The ratio of the perimeter is the same. They're the same. But then the ratio of the areas is 2/3 squared because it has twice the effect. So that would give you 4/9. And then the ratio of the volumes would be 3 times that. So 2 times 2 times 2 is 8. 3 times 3 is 9 times 3 is 27. Okay, so we got to work this one backwards. They don't give us anything, but we can undo this by square rooting. Square root of 100 is 10. Square root of 49 is 7. Okay, so the ratio of the perimeters then is 10/7. That is the same thing as the scale factor. The volume, though, we'd have to take that 10/7 and we'd have to do it to the third. So 10 times 10 times 10 is 1,000, and 7 times 7 times 7 is 343. So you just have to remember, you take the scale factor, the ratio of the perimeters is the same, the ratio of the areas is twice as much, and the ratio of the volume is 3 times as much. So we're going to do a couple examples. So it says a stop sign has a shape of an octagon with each side measuring 0.5. Let's see if I can draw one. So each side measures 0.5. To make a scale model of the sign, every dimension is multiplied by 1/20th. So if I were going to make a little tiny scale of this, I would multiply by 1/20th. So the new stop sign, the little tiny new stop sign, is going to have every side being 0.25. One, two, three, yeah. Okay, so it says, how is the ratio of the areas related to the ratio of the corresponding dimensions? Well, the ratio of the dimensions is just 1 to 20. So the new shape is 1/20th the original. Well, the areas, we know that that's going to be the dimensions squared. So this is going to be 1/400th. So I'm kind of answering both questions in one. So next one, a circular plate has a radius of 15 centimeters. And then it says every dimension is multiplied by 4 to create a larger similar plate. So the new is going to be 4 times bigger than the original. So it doesn't even matter what the actual dimensions are, because they don't really want us to give you the dimensions. They just want to tell you the ratio. So because you know how this affects, you don't actually have to give an actual volume or ratio. So how is the ratio of the circumference related to the ratio of the corresponding dimensions? Well, the circumference is really the perimeter. So they are the same. If the radius is multiplied by 4, the circumference would be multiplied by 4. So it says, what is the ratio of the circumferences? And I said, think of the circumference as perimeter, and it's just 4 to 1. Okay. This stuff might take a little practice. We'll see if we can dedicate some more time to it when you guys are in class.